So next slide, please. Okay. Today's session is co-organized by IEEE. Please welcome Dr. Aaron Chai, the Chairman of IEEE Power Electronic and Industry Applications Singapore Joint Chapter. He received his PhD in Electrical Engineering from NTU in 2018 and is currently working in Molex as a Principal Engineer. So, Dr. Aaron, please.
Thank you very much, Sharifa. So my name is Aaron, and let me give a very quick sharing about IEEE. So who are we? IEEE is actually the Institute of Electrical and Electronics Engineers, and we are the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Within this organization, there are 39 technical societies, of which power electronics and industry applications is one of the societies. Next, please, Sharifa. So what do we do locally? Firstly, we organize technical workshops and distinguished lectures. As you can see on the picture on the top left-hand side, this is a distinguished lecture by Professor Sun Kai and hosted by Professor Tang Yi in Nanyang Technological University. Next, please, Sharifa. We also organize social events for the community. So this is an event that we had in Gardens by the Bay 2 years ago. And this year, we will be having another social event as well. Next, please. We also sponsor book prize. So as you can see in the photo in the bottom right-hand side, there's a gentleman in the graduation gown and wearing a medal. He is our book prize winner, Warren Chan from Temasek Poly. Next, please. And what do we do internationally? We organize conferences. Next. So of which you can see APEC and ECCE. These are the flagship conferences for Power Electronics Society. Next, we also have publications such as magazines, journals, as well as standards, which you can see on the top right-hand side. Next, please. And we also organize competitions. As you can see on the bottom right-hand side, there's the programming competition, as well as some competitions which have a social impact on society, such as the Empower a Billion Lives. Next, please. So I will I'll urge you to join us. You can do so by signing up for an IEEE account, and you can add the please go to the previous slide. Sorry. You can add the Power Electronics membership into your cart, and if you are a first-time first-time registering for Power Electronics Society, you can use the promo code shown below to get a complimentary PALS membership. Next, please, Sharifa. So besides sharing about my chapter, I also like to share about an upcoming conference that the chapter will be organizing in Penang next year. So it will be from the 21st to 24th July in Penang, Malaysia. The food is great. The tourist locations are beautiful. So we urge you to join. So take note of the important dates from 15 January all the way to 30th of March. And you can find a lot more about us on the link below. Thank you. Back to you, Sharifa.
Thank you, Dr. Aaron, for sharing more about IEEE with us. Before we start, please take note of some reminders. Please ensure that your microphones and cameras are switched off. So don't worry, this session will be recorded and sent to you at the email address provided during registrations. So for those who'd like certificates, please submit our feedback form at the end of the session. And also feel free to ask questions in the chat. Our experts will address them at the end of the session. Okay, just stick to this slide first. So just a quick introduction, Texas Systems is the authorized reseller of Metworks products in Southeast Asia. Next. So our services include MATLAB, Simulink, SpeedGoat, and more. So next, please. So these are some of the vast array of solutions we provide. So you can take a look, and there's quite a lot of solutions. So yes, without further ado, please welcome your speaker, Romeo.
Hello, good afternoon to everyone. Okay, so I start sharing my screen. Thank you very much and good afternoon to everyone for being with us today. Um, it's a very good day for us to be here. Especially this is an event uh, organized by IEEE. So I'm Romeo Cabading. I'm an application engineer from TechSource. We welcome you to this webinar for the battery technologies. I'm also with Supamith, who is our lead application engineer from Thailand. So he will be helping me out in this case for answering your questions through the chat window. And later on, we will have a question and answer portion for this session. So hopefully we can have your questions through the chat, and then later on we can answer these questions for you. So before we start our session, I think there will be an entry polls that will be sent to you guys, so that we can just understand how our audience will be today, what kind of work that you do, and how you can apply what we will be talking about today, which is about design and simulation of energy storage systems, particularly using MathWorks tools, which is MATLAB, Simulink, and Simscape in this case. So hopefully this one will be very beneficial to you guys in this case. And hopefully you can join us for the next an hour and a half to share knowledge to each other, and then we can share what tools that we can use in this case. So while you're moving through the polls, I just like to maybe go through the agenda that we will be having today. Today we'll be diving into the process of modeling battery cells, where we can explore cell modeling techniques that we will be using through Simulink and Simscape. So from modeling, we will do battery cell characterizations, and then we'll study about, and then from cell characterization, we'll do a level up. In this case, we'll do a pack development from the cells that we have developed. We'll try to put it in a battery pack for development. So we'll simulate battery systems in this case and finally we'll look we'll have a comprehensive look at the battery management systems to ensure our battery life efficiency and longevity. If you have questions, please type in on the chat, and if time permits, we'll have a Q&A session with you guys to answer your questions. So what we will do today is I'll be jumping here and now from my slides and to Simulink MATLAB and Simulink tool. In this case, I will use a demo, some demos to show you how we will do it in actual tools that we will have been using. So I guess, okay, I'm going through the entry polls actually right now. I think most of you are intermediate users and have been using Simulink and Simscape in academic and research projects. So I think most of us are, asking for practical skills that will help us through designing our energy storage system. So I think that's a good way of how to say developing these systems that we have. We have it with MathWorks and MATLAB and Simulink. So okay, so to start with our discussions, I think every system designer would have every questions in his mind, whether an engineer or a researcher or maybe practically a student. So we'll have different questions in implementing in their systems. So questions that will guide them through their system design. So in battery systems, what we may be having similar questions that we have. So one question will be, can we model the battery in a simulation? This is how can we do a physical modeling virtually through our tools? So that's what we will answer also today. And how will our battery performance evaluated in the case for example, capacity, cycle life, efficiency? So how can we simulate all these questions and models here in our systems? And then how can we integrate these battery systems with components or devices, maybe in applications like much larger microgrid applications, or it can be also vehicle applications, which are now very rampant right now, for example, EV systems. And then how do we improve our overall thermal performances of our battery systems? So we'll try to evaluate and share with you how you can simulate these systems in your research or your study or your work. And finally, but not the least of them all, is what are the safety mechanisms we can do, or we can provide our battery systems to provide safety systems or safety mechanisms to allow a very good response in all applications commercially, or maybe in automotive or in any other industries that we are using these systems. So hopefully these topics or questions will be answered today, and hopefully we can share successfully these items. So for the agenda that we have today, so we'll start with this battery cell modeling. So I believe all these questions hopefully will give you an insight, and then we'll answer each questions that you have. So what I will do is I will try to go through with you through the slides, and then we'll go through some examples using this tool. So where do we start? Where do we start battery cell modeling? So actually, you have to decide what kind of simulation that you want to do with your systems. So this is called what we say simulation fidelity. Will depend. This one will depend on your selection on what type that you want to be in your simulations. Maybe you wanted a battery with an infinite charge, right? Or maybe because you are just interested in load power characterizations. But definitely you may want our battery systems that have finite charge or fade or temperature dependence, charge dynamics, and have cell behavior. So these are the things that we will try to discuss today, and then help you to decide which fidelity model that you want to simulate your systems with, battery systems with. So it can be with SOC, or you can have HPPC data that you have, that how can you use it to develop a model in your system, to develop the battery models that have very exact, almost equal behavior as an actual cell that is in the field. So we'll try to develop those systems with you. So as we said earlier, you can select using Simscape and Simscape battery, the model that you want to use for your fidelity simulations. So it depends on the fidelity that you want there in this case. So there are 3 types of these cell models that we have. Actually, we have 4 in this case. So in this case, Simscape battery allows you to have the fidelity. You can choose the fidelity of the testing that you want in your simulation. So I'll go through with you on this case to give you an overview of what are these cells and how can you use these cells in this case. So I'll demo a battery cell from Simulink and Simscape battery. So let's go through each one of the models that we have. So I'll be sharing the environment. Right now we are in MATLAB. So we'll open up a Simulink model using this command. So we'll open up a Simscape battery model in this case. Okay. Okay. So now I'm sharing with you one of the models that we have. You can open also Simulink library browser in this case, so that we can use Simscape models that we have and drag and drop them to your Simulink model. So I think traditionally we used to drag and drop models from Simulink browser from this case. So you can see Simscape can have a lot of physical modeling types that you can use. But for this time, we'll use Simscape battery to develop models from BMS models, which we will later on discuss. And particularly now we have the cells. So these are the examples of the cell modeling that we can use depending on your fidelity that you wanted to use. So in this case, we'll just try to put the battery here and then check out the battery systems that we can place in this case. So we have battery, the normal battery behavioral model. We have battery table-based model. And then we can also have battery. Okay, so actually now you can just type in and then we can have battery equivalent circuit. And then we also have another model, which is the battery single particle model. So one by one, we'll discuss each one of these, and then we can choose which fidelity that we want for each battery. So let's start with the battery behavioral model. So this is a battery behavioral model which we can use in Simscape battery. This is the simplest battery model that we can use, but it also have the capability of exposing the charge measurements ports and the thermal ports. So what do we have with Simscape battery is that you can specify the voltages of the battery or the battery pack that you are simulating, and then considering all those things and then putting internal resistances and dynamics in this case. Then you can also place thermal models in this case and then put eventually in your simulation. So this is one of the simplest low fidelity simulation models that we have in Simscape battery. Another model is a table-based model that we have. So battery table-based model is a high fidelity battery model, which calculates for the open circuit voltages functions, which is a function of a charge level and optional temperature with lookup tables. So as based on the name, so you will guess that this is model have tabular data that has all single charge. For example, we have a battery fade or charge dynamics, which you can use in later in the simulation. Another example is battery equivalent circuit. I think this is much more familiar to you in simulation, which uses electrothermal dynamics and optional faults that we can simulate. Actually, this is the most comprehensive model that we have that we can use from Simscape battery. This has electrodynamics using the battery, which calculates certain electrical elements with variable characteristics. And also it has tabulated variable characteristics that have in this case. So actually, if you see, there's a lot of models that is inside this model, battery model, which you can use actually specifically on each type of simulation that you have. So it can be electrical, thermal, or aging if you're concerned with aging. And then you can also do fault simulation for this example. So what we will do today is maybe let's do a small simulation of this battery system, and then let's see how we can use this battery simulation in our daily simulations for our work. So this battery equivalent circuit you can have has an option to put in available parameterized battery equivalent circuits in the market. So these have depends on the manufacturer that you want to use and is available for you to use actually. So actually you can select a battery that may be near to your model. So for example, let's use a Panasonic example and have a cylindrical type of battery model. So this is a lithium Panasonic lithium ion battery. So let's apply this one to our model. And then you can see that all the battery parameters are already inside in this case for you to use automatically using this selected part that we have. So from this, I think we can start our simulation. For example, we wanted a thermal model for this case, so we don't want to use a constant simulation. So let's try a lamp thermal mass. If you can see, there's already a model. The model comes out of the thermal model can be external to the system so that you can have a simulation for this case. So let's see if we can do a simulation, which is a charging model. So let's see a constant current. Sorry. Yeah, so we'll have a controlled current source for the charging source. And then we'll have a constant charging current. Let's say it will be a constant value. So maybe let's place it as -2 volts, 2 amps, I mean. So this is how we can create a small simulation circuit for our models. And we can interconnect these systems electrically. Any similar characteristics that we have can be simulated in this kind of simulation. So we can also place a voltage sensor to sense the cell voltage in this case. So let's do this and connect it to the system. And then the thermal model, I think maybe we can, as an example, we'll just use that. Let's assume that this battery is connected only through an infinite, an insulator, a perfect insulator. So let's try something like this and connect it to the system. So let's have a temperature sensor in this case to measure the temperature of the cell, and then let's have a thermal reference. Yeah. Okay. So I think with this we are ready to do some simulation. So in order for us to also check the SOC, which is an internal characteristics of the battery, so we can also place a probe in this case, probe. And then we can link this probe to the battery model, and let's select the state of charge of the system. So that's about it. And then we can connect all the parameters that we want for this simulation. So we just connect all the signals in this case to our simulation. So let's connect this one to this one. Okay. So let's rename the lines so that it's easy for us to In this case, this is cell voltage. And then this one is cell temperature. So, okay. So let's try to simulate this one. Given this one with the 3 parameters that we have, and then we'll put on the legend. Okay. So in every battery systems, actually, the simulation time, the 10 seconds actually doesn't really make sense for us. So actually this one, we can change to an hour or so. So for this, we will try to simulate 3,600 seconds. So that's about an hour for our simulation. So let's try this simulation and let's try to run it. So if you can see here, we have a measurement of our battery model in this case. So with this, we are successfully checking the SOC, for example, in this case. And we are also checking the battery voltage of this simulation. And then we can also check the temperature of this cell in this simulation. So what Simscape battery gives us is that we are able to simulate electrical systems in this case, and also thermal systems together with the electrical, and then we can estimate what our system behaves in a simulation environment. So this is one way we can do a simulation for our battery to give at least an overview of us to know what is the capability of the battery that we will be using. So if you are not confident with this battery, you can always change the battery type that you want depending on the manufacturer that you are using in this case, depending on the battery that you have. So I'll go back to this. I hope that this one is clear to you, and I hope this one is an example that we can use to develop battery systems. So I'll just go back to my slides. So we have discussed this battery systems, and then we have discussed different types of battery fidelity simulations that we can use for this equivalent circuits that we can use. So hopefully this one helps you in your simulations. So what if, so we have done our simulation based on existing libraries that we have in MATLAB, Simulink. But what if your battery model is not in that library, or maybe you are not satisfied with what how the model behaves in your simulations? So what you have is maybe you only have an initial battery model, which is not really behaving as what you have with testing with experimental data. So I believe what you will be having is HPPC testing specific for a battery cell, so that we can match this experimental data with a battery cell model. So let's talk about battery cell characterization. So we have several types of battery cell characterizations that we use with Simulink and MATLAB. One is this parameter estimation. Here we will show how to characterize a battery cell of any applications using this test method. So the hybrid pulse power characterization, which is an HPPC test, which you have performed, is a controlled environment chamber test. So a typical HPPC is a data that is coming from either a discharge or a charge pulses that have. So actually our model, this is an example of a discharge HPPC pulse that we have, and we can use for our parameter estimation. So in this simulation, what is happening is that we have several inputs on our model. So one is the model itself. which we have initially maybe selected, which have initial parameters, which is the voltage, open source, open circuit voltage, or open circuit resistances, and several RC levels. So this is the model that we have initially, but we wanted to compare it with our experimental data. This one becomes an input for us. So in the model that we can show later on, there's an output for this, which is the voltage. So in the experiment also that we have, we can also measure the voltage of the battery compared to the model. So what this model does is that it compares these simulation results. And then if the model has a very large error, then it does another iteration and changes the parameters that you have provided in this case. So until we are satisfied, or the simulation is satisfied by, depending on the tolerance that we have given it, then only then that the parameters can be saved to the model. So this is one way that we can characterize our model in Simulink and Simscape battery. So I'll demo to you how we can parameter estimate the battery cell using parameter estimation. And then I'll also show you how we can do a model-based calibration. Actually, this is a new way of parameter estimating this battery cell. So let me go back to Simulink, and then let me show you how we can simulate using parameter estimation. So let me just open my Simulink. Okay. So an example of this simulation is parameter estimation is this model. So if you've seen earlier, right, this is similar to what we have showed you earlier, which has the battery that is we are going to simulate. And then we have a current source that is being controlled by a set of data to charge or discharge the battery. And then we have another voltage sensor just to measure the voltage, or this is the output actually of the simulation. So this is very similar to what we have done earlier to estimate, to simulate the parameters of the battery. So let's take a look a little bit on the HPPT data that we have in this case, and then see how it is being used. So actually, this is a discharge HPPC example that we have. So if you can see here, actually, this is the response of a battery that is being simulated using actual battery, and then this is an actual measurement from that simulation. So it has a discharge current, and then the voltage of the battery is being measured. So let's take a look a bit of this graph and see how it is. If you can see, as the current as being increased through the charging current, you can see an instantaneous decrease of the voltage of the battery. Okay, sorry, I need to zoom in. Okay. So there's an instantaneous decrease of the voltage of the battery cell. And then there's exponential decrease afterwards after this simulation. And then when the current has gone back to zero, it goes back instantaneously also in this case, and then returns back exponentially to its normal open circuit voltages. So this is one example of how an actual battery behaves in this simulation. So let's show with different time constant or RC level. So this RC level actually it can be explained through the models that we have in this case. So maybe I go back to the slide that I was earlier showing. So actually this is the RC charge dynamics of the equivalent circuit that we will be using today. So it has the open circuit voltage, the EM, and the open resistance value or the DC value of this model, and the RC charge dynamics of the system. So this is the model that we will be parameterizing today. So let me go back to the simulation model, and then let's see how this simulation model can. So we'll just try to simulate and parameterize first with 2 time RC constants. So with this, actually, there are already the parameters that we wanted to parameterize or to equate with our model, and see how we can adjust the model's parameter. So let's do a single simulation. So you can see here two signals. One is the gray signal. This gray signal actually is the experimental value. So this is coming from your HPPC model testing. So, and the blue line is actually the voltage of the simulation. So there's really a gross error from the actual battery behavior than your simulation model. So we'll try to parameter estimate this model using this this so we'll try to use 2 time RC constants for this simulation, and then let's see how we can almost equalize the parameters, so that our model, we can have a confidence that it's almost similar as what we can do, or the parameters that we have in the actual battery behavior that is being seen through our HPPC test. So this is the one we are getting a challenge to do. So let's start with our simulation using the parameter estimation. So the parameter estimation is a tool in MATLAB where we can actually parameterize our system. So you can have experiments to be developed, and then you can select the parameters and have a sensitivity analysis in this case, but we'll not go through with it, but we'll just go through the parameter estimation. So let's start the parameter estimate in this case. So while it is running, actually another good way of using parameter estimation is actually we can also use the parallel processing of MATLAB, so that we can do multiple simulation at a time using the GPUs of our system PCs in this case. So this is one advantage that we can use to have a faster result in this case to simulate these kinds of parameter estimation. So now what it is doing is that is configuring the parallel workers or the GPUs in your system. So in this case, it is submitting the data or the simulations in your GPU and do the analysis on each of the GPU. So let's wait for a moment while this is running. And then let's see how the simulation and compare. If you can see later on, you will see the comparison of this actual data that we have from HPPC, and then how the parameter estimation help us to equalize this behavior in our system. So now I think it's starting to simulate and optimize. So for this simulation, actually, you can do there's still a workflow that we have. So you have to prepare your HPPC data that is there actually in your system, and then pre-parameterize this is your battery in this case. So actually now it's starting to optimize the results. So actually you should see a little bit differences in the simulation for the blue line and the actual testing data that you have. Yeah, so now it's starting. So actually, if you can see here, there's still a very large error, in this case about 9%. So, but if you can see, it's slowly starting to equalize with the expected battery behavior. So in the background, actually, it's slowly to calculate these parameters. Actually, if you didn't use parallel calculations or parallel computing, you will see that this actually updates every time. So you can see now it's the behavior of the simulation is almost equal to the simulation of the, I mean, for the behavior of the battery. So slowly that the errors in this case is being minimized based on the changes in the parameters. So this is how we can do a parameter estimation of the battery. Yes. So you can see that somehow it's already almost the same as the parameter that we are, testing the experimental value. Yeah. So you see that the errors are getting smaller and smaller, and that the simulation is getting almost the same as what we have in this case. Until it meets the specifications of tolerance that you have provided, the simulation will stop on that value. So actually, it's almost equal to your experimental value. So now the battery is almost the simulated battery is now almost behaving as similar to your actual battery testing values. Okay, so now the completed simulation. So I think we can see the simulated value that we had just run. So we can zoom in to the data that we see. So actually, there's still some errors that we see here in the simulated value. But if you go more time constants, maybe until 5 time constants, I think this behavior will be improving. So this is one way you can do a parameter estimation using this tool that we have in Simulink. So let me close this model, and then we can go through another model that we have. For battery systems. So let's try to do a model-based simulation. this model-based simulation is actually using automotive tools that we have in this case. So let me try to open up the app. We call it model-based optimization tool. So what we will use for this simulation is actually called feature filling. So we have a battery model that we have to be characterized in this case. So we'll just open it up. And then we will refer to some data that we have in this case. So we will have a PPC data that we have originally pre-processed, and then we can select that file that we have and then run another simulation in this case. So actually, this one will give us a parameterized value of this system. So let's try to run this simulation and then see how, if you can see, this is just a flat lookup table. So while it is running actually, so it does different iterations in the system. So you can see it reacts to each values that we have to match the HPPC data that you have, and then compares it to your battery model. And then actually this one does not do an experiment. Actually, it does a calculation to estimate the values that you are doing. So actually this simulation also compares the error that is being, the difference between the simulated and the battery testing results. So if you can see here, actually there's a big gap initially in this simulation, in the error. But as we go many iterations, actually in this simulation, it about 40 or 45 iterations, it will, the parameters that is not anymore actually changing, and then the errors are very minimized. So this is the case where we can actually accept this battery model that we already have. So this is one way to parameterize our battery, and then compare this one to our HPPC data, and then we can use this data, to model the exact behavior of our batteries in the field, so that we can be confident in the battery model that we are using. So actually, if you can see here now, at about 20 or 25 iterations, the change in the parameters are almost constant. So we'll just wait for a few minutes, and then I think we can see that it will flatten out later on. And then at about 40 iterations, it will flatten, and then I think we can accept the data that is being simulated. So it's almost at 30, level 30. So if you can see, it's already flattening out in this case. So at about 35 or 40, I think simulation will already stop. This is based on the root mean square minimum tolerance that we set in this case. So you can see the initial errors are larger than what we have right now when we have the 35 iterations that is being seen. So yeah. So now the change in the parameters are already flattened, and now you see that the change in parameters are constant, and there's very small change in it. So I think we can accept the data that is being simulated in this case. So yeah. Yeah. Okay. So now the information that we have has been changed actually. So initially, if you saw earlier, this was a flat table. So now it has been filled with the correct values that we can use for our battery simulation. So this now becomes almost an exact replica of your battery model. So that is one example of battery characterization that we use in Simscape battery for this system. So let me move on to the next slides that we have. If you have further questions, feel free to type it in the chat so that we can answer your questions. So hopefully this one helps you in our development. So now that we are confident with our model, so what we wanted to do is to level it up. Now, because we have tuned the parameters of our battery cell, now that we are very sure that it behaves similar as what we have in our systems. So what we now want is to develop a battery pack for our systems. So in Simulink, we have this tool called Battery Builder app. So we can construct a battery pack model using this battery modeling app. So actually, you can see here in the video, it's so fast. But actually, later on, we can show you how we can do a battery model to simulate what we have for a given requirements that we can do. So this creates a library for us, for you to use in your simulations. So let me show you how we can develop a battery pack model for you to use. So we have a battery modeling workflow. So initially we will have a cell. So the cell initially we have done previously. So now we have confident that the cell model that we will use will be almost similar to what we have in the field. And then we will create a parallel assembly to create the capacity of the battery. And then we'll do a module level assembly, and then module assembly, and eventually to the pack. So this is the workflow that we have to develop this battery system. So what Simscape model have is that actually we can do also an API. So it can be programmatically or it can be using the app. So this battery model app has an external .mat file that you can use later on to develop your system battery pack programmatically. So let me show you how we can develop a battery pack system. So in this example, we have a battery specification. For example, we have a 48 volt with a capacity of 50 amp hour. And then we have a cell capacity. Each cell will have a 2.5 amp hour capacity. And then let's just assume that the battery voltage for each of the cell is 4 volts. So for this example, so with this calculation, actually, we will do a 20 parallel combination, and then we'll have a 12 series combination of this module. So we will do the cell modeling, and then we'll do the parallel assembly, and then we'll do a series of this parallel assembly to build up the voltage that we need. So that is 48 volts. So for this example, I wanted to show you that each of this parallel assembly actually will just do a 5P in this case. So 5P, 5 in parallel, and then we'll make 4 modules for this battery pack to meet the 20P requirement in this case, which is this one. So we'll have 4 of these parallel assemblies to make the pack. So this is the module. and then we'll have a module assembly, and then eventually we'll have a battery pack. So with this app, we'll try to develop this battery pack for our systems. So let me show you how we can develop this through MATLAB. So in MATLAB, we have, okay, let me go back to home. And then we can use the battery builder app. So this is the battery builder app here. We can show you that I can show you. Okay, sorry. So let me open the app. Okay. So actually here you can already see the workflow that we have initially said earlier for you. So we start with the cell, then we start with the parallel assembly, the module assembly, and then eventually the pack. So let's try to make the cell cell. So we just need a name for it, and then we'll try to place maybe a new cell, and then we'll what kind of geometry that you wanted to use. So let's say we'll do a cylindrical type. Then the capacitor earlier, we said it's 2.5. So using this value, we can place here, and then what kind of parameterization that we want. Initially, we used Panasonic, or you can use any other cell that you want, especially if you have already characterized what your data is. So you can use actually this one to do the cell combination. So we want what kind of fidelity that you want for your testing. So maybe we want temperature dependence. Let's say we have a thermal port for this. So let's just click apply. So what Battery Builder does is that it gives you also a 3D representation of your battery pack. This enables you to visualize your battery in this case. So since this is just a cell, so we'll try to do a battery a parallel assembly next. So let's do a parallel assembly. So earlier on, we said that we wanted a 5P for each module. So we'll put in a new cell, the one we created earlier, and then we'll have 5 in parallel. So we can use this one for our modeling. So let's say we want what kind of resolution that we want for this model. So we can just, it depends on you, what you want as a simulation in your simulation model. So you can have detailed or lamp. In this case, we won't change this thing. In this case, if you want thermal models, you can also click and have these thermal models to be out in your simulations. So depending on what you want, you can use this simulation kind of fidelity. So this is, let's say we have already created a parallel assembly. Now we wanted to go to a module assembly where all these one are being combined. So let's say we have create a module assembly. So we'll just specify which parallel assembly we will use. In this case, we'll use the previous one that we have built. And then since we have discussed earlier, there are 12 series cells that we are using in this case. So we'll just apply, and then we'll just see, okay. So this is a wrong orientation. So this is for the stacking axis. So let's change to X. So this is what we want. So this is the parallel assembly. And then there are 12, this parallel assembly will have 12 series to complete the 48 volts. So this is the new module assembly that we have. So next we will select the module assembly that we want, and then again, create a module assembly from the modules that we have initially done. So there are numbers here that very interesting. So maybe this one is a concern, a good way to explain. This is about the intermodule gap. So I think this one is about for your thermal analysis, so that you have some spacing between the modules of the parallel assembly. So you can do this and then build your module. So in this case, you see there's a gap in between the modules. So this is the number that is being admonished in this case. So from this module, we'll create the pack. So let's create. Finally, there will be 2 module assemblies that we need to complete the pack. And then there will be some kind of intermodule gap in between because of your thermal considerations. So you may want also, depending on your simulations, if you want balancing strategies that you want, it can be passive or external. You can specify in these simulations, and then you can also specify the thermal simulations that you want this model to have. So for this case, we'll just go through this and then we'll build the pack. So this is the final version of the pack that we will be using in this case. So you already have a visual of the pack that you have developed, and then you can use this simulation as for your simulations. So now we will create the battery pack model in this case. So maybe we'll just save it to the, okay, and then we select the folder, and then let's say my batteries to create the battery. Okay. So what it does actually is it creates the library in this case for your battery. It creates the library. It creates the SSC files or the Simulink Simscape language files. So eventually you are able to use this battery model for your simulations. So this is the final battery model that we have that you can use later on for your simulations. So in the interest of time, I'll just move forward again. So we'll just close this battery app. Yes. So let me move forward for the slides that we have. So now we have developed the battery pack that we will be using for our systems. So this is one, the one I'm showing is actually using a program or a script to develop the pack. If you are not really keen into using the app, if you are doing a lot of modeling, then you can use the Simscape battery API to do this modeling. So the one I showed earlier in a video is that you see this is programmatically developing the Simscape battery pack that you can do. So it programmatically do this API applications for you. Okay, so to add more in this case, you may want also to consider the thermal simulations that you have. So there are several types of fidelity that you can use for this simulation, for the thermal simulations. You can use a lamp, grouped, or detailed. Detailed meaning each of your cells will have a model, a thermal model in this case. So there are different battery pack thermal connections that can be used for this simulation. So one is intercell heat transfer. This is in between the cells inside the pack, and then you can have an ambient connection in this case, and then you can also have a coolant or a cooling plate to connect to this thermal model. So this one gives you a simulation that is almost in the physical level, that you can actually control a coolant, or for example, and then have a coolant plate for your simulation. This one gives you a variety of testing in this case. So there are certain types of coolant plate connections that we can use. We can use parallel channels, edge cooling, U-shape type, and configure channels, number of channels that we have. So these are the simulation thermal models that we can use for this battery pack development. So you can choose how many channels that you have for your cooling plate where the coolant is flowing. So you can simulate actually very detailed or in a group systems. So this is one of the simulations that we can do in this case. So we can adjust granularity of the plate and connect the pack on any resolution. So hopefully this one helps you in this case. Okay. Maybe I can just go through first on the battery management system, and then later on we'll have a question and answer if that is the case because of the time that we have. So we just have a little bit like 20 minutes to do. So maybe I can, with your permission, I can go through the simulation of the battery system so that we can eventually later have a question and answer. Okay, so battery management systems. So what are battery management systems that we can provide here in so Simscape battery includes Simulink blocks that can perform typical battery management systems. So these battery management systems actually can estimate state estimations or battery protection, or you can use it for cell balancing, thermal management, current management. So these are the categories that this BMS can be used. So in this case, you really don't need to do a logical program to do these simulations actually. So what it does is Simscape battery gives you an initial how to say models for you to develop your BMS. For example, we don't really have, for you as an engineer, maybe you don't really have yet an idea how we can do the BMS. So might as well this battery system BMS that is provided by Simscape battery, you can eventually develop your BMS with through these libraries. So without even designing some of it, so we just have to put the variables that is needed by each of the algorithms. So we have several types of this battery management algorithms. So we have charging and discharging control. We have battery cell balancing, and then we have the battery state estimations. We have the state of charge and state of health. So in this case also, we can have a battery protection, either over current or under voltage or over voltage or temperature protection. And then we can also have a thermal management of the battery itself. So these are the models that we can use in Simscape battery for our applications. So this is an example of the charging and the discharging blocks that we can use for controlling the charge and discharge of the systems, battery systems that we have. Then, as I said earlier, you can have your model to have a balancing systems, cell balancing system in this case. So we can add this module to control our cell balancing blocks in your battery systems. And then there is also what we call state of charge estimation. State of charge is cannot be actually measured externally on the battery. So we have this Kalman filter to estimate this state of charge of the battery itself. So we can use these systems to develop your battery systems. So we also have the battery protection algorithms that is there. We can do battery monitoring, battery voltage monitoring, temperature, and then fault qualification. So actually, you can put all your sensors in the battery. It can be interfaced with these libraries that you can use. And eventually, you can also use thermal management for either cooling the battery or heating the battery, depending on the temperature or the ambient temperature that the system is being used. So in this case, we have a coolant control or a heater control for this application. So you can use this battery thermal management system to develop your initial start as developing the battery management system. So let's have a demo for the battery management system. So let me go back again to the tool. So what I will show you this time is, okay, maybe I'll use, okay, let me, okay, sorry. So what I have here is, as an example, is an EV electric vehicle battery charge and discharge protection. So this example actually gives you an overview of how you can actually protect your battery during charging and discharging. So this one have a capability of actually simulating your thermal response based on charging and discharging of your battery. And then you can have a BMS actually within that battery. So actually, for all that we have discussed earlier, from cell development to pack development and the battery management system, so all this can be combined in one application. It can be electric vehicle, it can be microgrid applications where you have the BMS and the battery itself also. So these are just one of the examples that you can use for this simulation. So actually now I'm running the sim. So actually you can see here, you can, with the dashboard, actually, you can see the simulated results of your system. So this is one way of multiple physical types of simulation. So one is thermal, another is electrical. So all this can be simulated in your systems in this case. So this is one example of a BMS application plus the pack battery pack examples that we earlier done in this webinar. Okay. So maybe I go back to the explanation. So this battery pack has some modules, and then this is actually the modules that within the system itself, and then it helps you to visualize actually the simulation using dashboard. So this is coming from MATLAB also in this tool, so you can use to visualize the data or the information that you have. This example also utilizes the BMS in this case. So this one helps you to develop actually how you can integrate the system in this, for example, EV application. There may be other applications that you may have in this case. It can be a microgrid, as I said earlier, or you can be simulating renewable energy plant models that have maybe solar photovoltaic systems plus battery systems. So actually you can combine these systems using Simscape and Simscape battery to develop your battery systems and improve doing tests for your battery management systems. So this model also do SOC estimation using the extended Kalman filter. So all of these examples are available online. Actually, we have a lot of examples that we have actually for this case, different applications of battery management system. For example, peak management, peak shaving. Peak shaving is used for renewable energy system. This one is particularly using solar PV, solar photovoltaic. So yeah, there are several examples. So you can see we don't really have to start from zero as an engineer. As we are developing our battery systems, we can have some references using MathWorks examples. So okay. So hopefully, I think I will end here with the key takeaways that we have. So we have shown you battery modeling using Simscape battery. And then we have done battery cell modeling and characterizations using cell parameter estimation. And then we have developed and moved up from a cell to a pack development using a battery builder app. And then eventually this battery and this battery pack, we integrate with the battery management system. And thus we have our own battery systems we can do in our simulations. So hopefully this sharing have helped you in this case to develop and study your battery systems that you are doing in your work. So we'll have all this documentation for Simscape battery online, so you can have a reference for this case. And then MATWorks also provide self-paced training for eventually if you want to do a training for even the battery builder app has a training also for this case. So there's also an instructor-led training that you can talk to us about. And then this is a 2-day training which has cell characterization and all those battery model pack development. So there are a lot of upcoming events. I think our marketing guys can share
Yes,
this
hi.
one. Yeah.
So thank you, Romeo, for the insightful presentation. If you enjoyed this, do follow us on our socials and head to our website to find out more about our upcoming events, webinars, and also if you'd like to learn more, you can reach out to us for consultancy and training services. So please participate in our exit poll and submit your real name and email address if you would like to receive a certificate from us. You can also leave a feedback to tell us what you'd like to learn more. And also, if you're interested, we actually have a webinar coming up next week for software-defined radios. So it's actually several sessions. So it's starting next week. Let me